So let's start off with some sample diploma questions. And yeah, one difference between gravitational fields and electric fields. Okay, let's get the pen out. Gravitational field strength depends on the mass, but electric field strength does not. Yeah, that seems right. Gravitational fields can be either attractive or repulsive, but electric fields are only attractive, so that's opposite. That should be if you switch the titles. That's not correct. The measurement for gravitational field is Newton per Coulomb, while electric field is Newton per kilogram. We haven't learned that yet, but that's opposite. And gravitational field strength depends on the distance between objects. Electric field does not. That is incorrect as well. So yeah, A looks like the correct answer. 2, there's past evidence of volcanic rocks that Earth's magnetic field has changed drastically in the past. Which of the following diagrams provides an accurate representation of Earth's present-day magnetic field lines? So not these guys. Magnetic field lines go in a loop, and the field goes towards the North Pole, which is actually magnetic south, but geographic north. So C is the correct answer. And the South American electric eel can produce low voltage discharge to detect prey or high voltage discharge to sun prey. So if we want to know the electric field lines around the eel, so we'd have to look at what Pedro would do, and Pedro would go from positive to negative like that. So B would be the correct answer. Yeah. Okay. So I didn't really have an assignment with that one because that's fine. Okay, calculating fields. So we're going to describe electric and gravitational field strength using these formulas and use those equations. So gravitational field strength. So what do you think happens to Earth's ability to pull in masses as they get further away, right? If I had an object here or I had an object here, well, which one do you think would be stronger? Well, this one would be stronger. The closer you are, the easier it is for Earth to pull it in, right? So as your distance gets bigger, your field gets weaker. So when one gets bigger and the other one gets smaller, we call that an inverse relationship, right? So as one goes up, the other one goes down. So if we wanted to graph an inverse relationship, this is what the graph would look like. So if we have field strength here, that's a symbol for field strength, and then we have distance, which we use R. Down here, we can see that when we have a very small distance, we have a really big field strength, right? When we have a really big distance, so this would be a bigger number up here, we have a really small field strength. So this is what our graph would look like, and you need to know what that graph looks like. So what's better at pulling in things, the Earth or the Moon? So if we had an object directly in between, which way would it go to? Well, it would go towards the Earth. Why? Because the Earth has more mass, it's bigger. So the gravitational field strength has a direct relationship with the mass creating it, right? So this has a really big mass, and it has a big field strength, and this one has a small mass and a small field strength. So as one goes up, the other one goes up. As one goes down, the other one goes down. That's a direct relationship. And this is what a direct relationship would look like. If this was our field strength and this was our mass, if we have a really big mass here and a really big field strength, if we have a small mass, we have a small field strength. So you need to know what those graphs look like. So this is our formula for field strength, where G is our gravitational field strength, and these are the units that they're given in. Big G is a constant. It's a universal gravitational constant. It's just a number that's always the same, kind of like pi is always 3.14. It's the same idea. M is the mass of our source, and R is the distance from the center of our source. Okay, so that's our formula, and you can find that formula right here on page 2 of your data booklet. And this big G is always this value here. It's always 6.67 times 10 to the negative 11. And what you could do is you can actually store that number in your calculator if you wanted. So if you want to store 6.67 times 10 to the negative 11, so that's times 10 to the negative 11, you type it in like that, and then you push this button, STO, store, with the arrow, an arrow will show up there, and then we want to save it as G, so we'll click the alpha button, and then we'll click G, and look at that, it's saved in there. So now if I go 2 times alpha G, it'll just multiply that number by 2, and it knows what G represents. So we have that in our calculator there, which is helpful. Okay, so calculate the gravitational field experienced by someone standing on the surface of the Earth. So we need to know a few things. Okay, so we know what G is, but it doesn't actually give us any numbers here. But if we look back at this page, we can see that, we have the mass of Earth. So it might not always give you information about Earth, but you have it on your data booklet here. And then the radius of Earth, well, if you're standing on the surface of the Earth, right, if you're standing right here, this is you, you're standing 1 radius away from the center of the Earth. So we have that information in our data book, right? So all this we have here, so we're going to use 6.67 times 10 to the negative 11. Our mass is our mass of Earth, which is 5.98 times 10 to the 24 kilograms. And then our radius is 6.37 times 10 to the 6 meters. And you have to remember to square that number, right? If you forget to square that number, you'll get it wrong. Okay. So if we want to plug this all into our calculator, this is how I would type it in. So you want to put the top in brackets. So, I guess we can just go G. So we go alpha G. We got that typed in. And then we want to multiply it by the mass of the Earth, 5.98 times 10 to the 24. And then you close your bracket up top. And on the bottom, we want to open a new bracket, and we want that 6.37 times 10 to the 6 in there. And then we want to square that number, and we can close our bracket. And if you type that in, you get that, which is pretty close to the gravitational field strength on Earth. Okay. So how far away from the sun would you need to be to experience the same gravitational field as someone standing on the surface of the Earth? Okay, so this one we need to rearrange. So we want to find a distance. So we want to find this R. So the first thing you want to do when rearranging a formula is you can always move things diagonal. So we can move the R squared up top. And we want to do that first because we want to get that R up top. If we don't get it up top, then we'll get the inverse, which is not what we want. And then we can move the G down below, like that. And then to get rid of this squared, if you square root both sides, that will cancel out that. And we end up with R is equal to GM all over little g square rooted. Okay. G is going to be the same. That's at 6.67 times 10 to the negative 11. And sun, we need to know the mass of our sun. So if we take a look here, oh, look at that. It's got the mass of the sun in our data booklet. So 1.99 times 10 to the 30. Okay, and then we want to use our answer from before. We want to use our calculator answer that we got here, 5.9829, or 9.9829. Oops, I think I said that wrong. 9.829. 9.829 meters per second squared, or newtons per kilogram. We want to plug that in there. Okay, so I'm going to show you how to type this into your calculator. So again, we want to put our top in brackets. So we're going to go alpha G, and we're going to multiply it by our 1.99 times 10 to our 30. Oops. Times 10 to the 30. We close our brackets up top. And on the bottom, I want this answer. So I can just go second negative, and it'll plug in that answer from before. And I want to put my bottom in brackets. So it's always good to put your top in brackets and your bottom in brackets like that. And we have to square root our answer. And I always like to do that in the second step. So I'll square root my answer from before, and I get this. So that's how far away I'd have to be. So if I wanted to express that in scientific notation, it'd be 3.67. What was it? I forgot. 3.67 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9 meters away. Okay, that's how you do gravitational field. Okay, so try out this board question, pause the video, see if you can do it yourself, and then, yeah, we'll go from there. So if the moon has a mass of that and a radius of that, calculate the gravitational field strength. So, yeah, pause the video, see if you can do it. I will do it as well. Okay, so I'm ready to type that into my calculator. Let me just make this a little bit shorter here so I can see. To go a little bit shorter. Oh, I can't go any shorter. Okay, I'll have to remember it. Actually, I can see it here. Okay, so we would plug in alpha g, and then we would multiply it by the mass of the moon, 7.35 times 10 to the 22, close our bracket, and divide it by a radius. And if you got the wrong answer, a lot of people get the wrong answer because they forget to square the radius. So make sure you square it like that afterwards, and we get a value of 1.62. Okay, so is this bigger or smaller than Earth's value? Well, we calculated Earth to be about 9.8 meters per second squared, so it looks like it's a lot smaller. So why do you think it's smaller? Well, the main reason why is because the mass is so much smaller, so that's why it's got a smaller gravitational field. And I hate mindless calculations, so what does this gravitational field mean? Well, it has to do with what gravity looks like on the moon. Let me turn that down. What gravity looks like on the moon. So you can see how they move on the moon. Sorry, let me just switch to my pointer. Yeah. There we go. So you can see how everything looks like it's slowed down. They can hop so much higher, and that's because it has such a small gravitational field. And he's going to fall down in a second here. Wait for him to fall down.
It was almost dangerous. You lose sight of the fact that it's a vacuum out there and it keeps running a leak next week.
Here he goes. So he falls down here, and look how he gets up. Imagine trying to do that on Earth, right? It's because you get that small gravitational field. It's like less of a force when you're in there pushing down on you. Okay. So, let me get my pen back. If you want, it should be want. If you went double, oh, no, it is went. If you went double the radius away from Earth, what would the gravitational field be? Well, so if we use G equals GM all over R squared, and we just did G, we did the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. And we want to go double the radius, so we'll go double the 6.37 times 10 to the 6 meters. We want to make sure our squared is outside of our bracket this time. So let's plug that in. So go alpha G times 5.98 times 10 to the 24. And we'll divide it by 2. 2 times the radius, 6.37 times 10 to the 6. And we want to square both those numbers. So we want to make sure our squared is outside the bracket this time. And we get this. Okay, so if I go our answer from before, which was like 5.83, it was like 5.82-ish, and I divide it by this answer, you can see it is basically 4 times less, right? What if you went triple away? Well, there's a pattern to this, right? When we, let me switch my colors here. When we double the radius, what happens is this double gets squared. So we're not making any changes up top, but we are making changes to the bottom, so we end up quartering it, right? And if we tripled it without doing any calculations, so I did g equals gm all over r squared. So if I end up tripling this squared, right, I'm not making changes up top, but 3 squared is 9. It would end up being 1/9 as big, right? So if you double the radius, you get 4 times weaker. If you triple the radius, you get 9 times weaker. If you quadruple it, you get 16 times weaker. If you 5 times it, you get 25 times weaker, right? Because if you double, we have to double that squared. Triple squared, right? 4 times squared, which is a 16. 5 times squared, which is 25. So that's what happens. And there's questions like that that you need to know as well. Okay, what can create an electric field? Well, we know that to be, let me switch my color back to black, a charge. How do you tell the direction of the electric field? Pedro! What happens to the electric field as you get further away from the source creating it? We know it gets weaker. So this is our formula. It looks super similar. We have our electric field. We have a constant. So instead of G, we have K, which is Coulomb's constant, and has this value. So we can store that Coulomb's constant in our calculator. Let me make this a little bit bigger. So we can store 8.99, times 10 to the 9, times 10 to the 9. So we want to store that, so we push store, and we can store it as alpha K if we want. And now it knows what alpha K is. So charges in coulombs, distances in meters, it's really the same thing, right? So let's do an example here. Determine the electric field 90 centimeters north from a 9.5, ooh, what's this? Microcoulomb. Remember that that's micro, which is times 10 to the 6. So if I wanted to do that question, so let me switch to my board here because it's a little bit easier. So determine the charge 90 centimeters north of a negative 9.5 microcoulomb charge. So this is 9.5 microcoulombs. So we have, we want to know at this point right here, what's the field at? So we can use electric field equals KQ all over R squared. So our K is our 8.99 times 10 to the 9 newtons per coulomb, or sorry, newtons, meters squared per coulomb squared. Our charge is 9.5 microcoulomb. So instead of writing micro, I can write times 10 to the negative 6 coulombs. And then we are 90 centimeters. So instead of writing 90 centa, I can look up on that same chart and I can see, what is centa equal to? Well, centa is equal to times 10 to the negative 2. So instead of writing centa, I can write times 10 to the negative 2. Right? And I have to make sure that I square that R value. So if I plug that all into my calculator, so I'll go alpha K. So I want to put a bracket in there. So alpha K times 9.5 E negative 6 times 10 to the negative 6. And then on the bottom, we have 90 E2, and we'll square that. And yeah, that's what we get as our answer. So, oops, sorry, that's not our answer. I screwed up. It should be times 10 to the negative 2. I was like, that doesn't seem like the answer. So, sorry, it should be E negative 2 squared. And then that's our answer. So we end up getting 1.05 times 10 to the 5 newtons per coulomb. Those are our units. Okay. So we got a couple more questions and then we're done. What is the charge of an object giving off 43 newtons per coulomb, 30 centimeters away from our object? Okay, so let's do this one. I'll switch to this again. So we're going to be using the same formula, but this time we're trying to find charge. So we have to rearrange it. So we can move the r squared diagonally up here, and then the k diagonally down there. And that's how we'd find our charge. So our distance is 30 centimeters, so times 10 to the negative 2. Our field is 43 newtons per coulomb. And our charge is 8.9, or our constant is 8.99 times 10 to the 9 newtons meters squared per coulomb squared. Okay, so I plug all of that into my calculator here. So 30 times 10 to the negative 2 times 43, and I divide it by my k value. So alpha k, and I just realized I made a mistake here. In the formula, this r is squared, so I have to square that r value as well. So I'll go back and I'll insert a squared there. There we go. So this squared times 43 divided by k. There we go. And our charge is 4.3 times 10 to the negative 10 coulombs, right? Or we could write it as 43 nanocoulombs, because if we move the decimal place over one spot and we go, that would be times 10 to the negative 9. You could answer it both ways. Both would be correct. Okay, so that's it. I will post an assignment. The assignment has answers, so I don't need to go through it. So let me know if you have any questions, and that is all.